Hey Cooper 6, welcome to our last set of benchmark notes for the year. We're going to break these benchmark notes into two parts. The first is going to be about energy transformations and conversions, along with renewable and non-renewable energy. And then the second part of the benchmark series is on the sun, moon, and earth interactions with each other. They're going to be related, but you probably won't see the connection until a bit further into the second part of the benchmark lesson. But before we get to any of that, let's get started. This is the Unleashing Sunlight benchmark. And the idea behind unleashing sunlight, hopefully will make this clear to you, is that the source of most of the energy that we use on Earth, it comes from the sun. Whether it comes directly from the sun immediately, or it is caused by the storage of energy from the sun over millions of years. Sounds weird, but we'll get to it. Sun is the cause of and source of the majority of energy that exists here on Earth. So we're going to take a look now at the human population growth graph. Right? It has some significance because it talks about the amount of energy that we as humans need and the amount of people that we have on Earth at any given time during the year. And you see that over the past several hundred years, the population of Earth has been relatively steady until right around the 1900s. And then around the 1900s, the population of humans on Earth has just shot up like exponentially in a tremendous amount, to the point where we're starting to have to wonder and worry about whether we have the resources necessary to take care of everybody. So in order to sort of point out the significance of that, let's start talking about energy. This unit in particular is dedicated to learning about how energy moves or is transferred from one type of energy to another. Okay? And we have the law of conservation of energy, which says that energy cannot be created or destroyed. Okay, so all of the energy that we have is all that we're ever going to get, and it's not going to go away. And even though we think that that might sound like a great idea, hey, none of the energy that we have is ever going to be destroyed, right? It usually ends up getting converted or transferred into forms of energy which we cannot reuse. So it says here, most of the things we use energy for result in that energy being converted. Converted is a fancy word for changed. Converted into heat. Right, which cannot be reused, and that's the problem that we deal with, is that yes, that energy is not being destroyed, but it is being turned into heat. And once we have energy in the form of heat, there's not too much we can do with it other than warm us up. And at that point, it just sort of spreads out and disperses, and we can't capture it again to reuse it. All right, so taking a look here. Here are some common energy conversions that we use as humans. So we have chemical energy from the food that we eat. Right? Whenever we eat food, there's potential energy in that food that we use to break apart some chemical bonds, which is where that potential energy is stored, and we release that energy, right, to be used for any number of biological purposes, like movement or thinking or pumping blood or breathing. We also have the idea of chemical energy, which is a lot like the chemical energy we find in food, but the chemical energy we find in batteries. This is stored potential energy that we can release, right? And in this case, we're using it to use a flashlight. Other forms of energy we can use are electrical energy. Another way for us to get light or to get things done is to use electricity. We have a more stored potential energy, not in batteries or in the food we eat, but in some of the petroleum products that we use, like gasoline. And we burn the energy in that gasoline to release it, right? And then we use it to drive our cars. And here we have sunlight. Right? Sunlight is another way to take energy and store it. So we take that sunlight, just like with the theme for this unit, that sunlight is used by plants right, to do photosynthesis. We talked about that in our last unit. And that photosynthesis allows for the plant to grow and store sugars inside of it to be used as food. And finally, we have the idea not just of using electricity to get light, but also to heat things up. So you see a picture here of electricity being used to toast some bread. So we're going to move forward here and talk about the different types of renewable and non-renewable energies. But let's fill this in here. Let's take a look at the different energy transformations. Energy transformations. Because back to the law of conservation of energy, we don't actually lose any of that energy. It just gets transformed, or, right, we can use this word again, converted to different forms, right? And sometimes those forms of energy, like I just said, heat, we cannot reuse them once we have used them up. All right, let's talk now about different sources of energy and whether or not those sources can be reused quickly or they fall into a category of non-renewable. Non-renewable energy sources cannot be replaced after they're done being used, or they actually take millions and millions and millions of years for us to get them back again. And the greatest example that we use all day, every day in our lives, for the majority of us, are fossil fuels. Right? So the idea behind fossil fuels is that millions and millions and millions of years ago, when dinosaurs roamed the earth, we had plants and animals, and they died. And when they died, they just kind of fell where they were and sort of decomposed. They rotted in the ground, and layers and layers of soil fell on top of them over a very long period of time, which either squeezed those remains into solid chunks, or they decomposed and liquefied, or there were gases released from them, and those gases got trapped underneath the soil. So you have these chunks of decomposed dinosaur and plants, or liquefied goo, or some gases trapped under the earth that we have, as humans, figured out how to pull out of the earth and use as a source of energy. So an example here of the solid chunks is coal, all right? We dig up coal from coal mines and then refine it or burn it to release the energy stored in chemical bonds. If you've ever used a charcoal grill, that's the idea, is that charcoal gets heated up, and as the heat begins to break down the chemical bonds between the different carbon atoms in the coal, it releases lots and lots and lots of energy that keeps a fire burning. Right, we, in many cases, to get electricity, which sounds a bit strange, burning coal eventually leads us to getting electricity. We start our basic step with burning that coal to boil water and make steam. We're going to talk a little bit about why steam is essential for us to get electricity in just a sec. But another source of this non-renewable fossil fuel energy besides coal is petroleum. Okay, and petroleum is a fancy word for crude oil, right? And that crude oil can take several different forms. Petroleum itself can't be used very well to burn and release energy. We actually have to refine or distill petroleum, where we boil it and separate the different parts of it because it's a mixture. And one of the parts when we boil it is diesel fuel, which sometimes there are vehicles like big trucks that use diesel fuel. You can get gasoline. You can also get many different types of oil that are used in car motors and engines. And finally, if you are familiar with it, look at a bottle of Vaseline, and underneath it you'll see that it says petroleum jelly, right? One of the byproducts of refining or distilling petroleum is to get Vaseline. So that comes from, well, the dead dinosaur goo. It's not necessarily a dinosaur, right? It could be plants or other animals from way back when, millions of years ago. But it essentially does come from that. And if you've ever seen a gas station that says BP, the B stands for British, and the P stands for petroleum. Okay? And one final way of using fossil fuels to get electricity, and remember all of this comes back to burning something, and usually burning something leads to boiling some water to get some steam. So one other way of doing that is to take natural gas. Okay. So again, sometimes when these dead dinosaurs or plant matter died and began rotting, they let off gases. And we use those natural gases, right? We pull them out of the ground, and we use them to cook our food and heat our homes. So if you have a gas stove, right, when you turn the pilot on and you hear the clicking sound and then the blue flame pops, that's natural gas. And natural gas doesn't actually have an odor. It's kind of dangerous in that respect. But Con Ed or any other power company will actually add a smell of sulfur to it to warn you. So natural gas doesn't actually smell like flatulence. They add that odor in from the sulfur, which is why you smell that same thing from like an egg yolk, from a hard-boiled egg. But this natural gas is usually used to burn right away to heat our homes. So why burn these dead dinosaurs and rotted plants from millions of years ago that we dug up from the ground? The idea here is burning coal or burning fuel oil or burning natural gas will heat some liquid water, and it will turn that water into steam. And steam has a lot of kinetic energy, right? So that steam is used as kinetic energy, right? Moving, flowing kinetic energy, which turns a generator. Okay? And a generator is made of an electromagnet. Right? That's a magnet that we spin around and around and around super fast near a bunch of coils of wire. And the result of spinning that magnet around the coils of wire super fast is that it creates an electrical current. So that steam that we got from boiling that water is forced down pipes at a very high speed, and they basically end up pushing, that steam pushes a magnet around and around and around and around inside of lots and lots and lots of loops of wire, and that wire starts creating a flow of electricity. And that flow of electricity will leave the power source, usually some kind of power plant, and head out along wires on streets, eventually to your home. So let's back this all the way up. It sounds kind of strange, right? The use of oil and coal and natural gas boils down to, in the most literal sense, to making steam, which creates electricity because it helps a generator spin. But let's go further back than that. Where did the energy from the dinosaurs originally come from? Now we have to fold in some of our stuff from the ecology unit, right? So let's think of a Tyrannosaurus Rex, right? A Tyrannosaurus Rex is a carnivore, right? So it's a consumer, and it gets all of its energy from eating other dinosaurs or other living things. Now let's back that another step up. So a Tyrannosaurus Rex could eat another carnivore, or it could eat an herbivore, right? Or even an omnivore, an animal that eats plants and animal products. But let's say, for the sake of this discussion, that the Tyrannosaurus Rex eats a brontosaurus, right? A big, huge dinosaur that eats only plants. It's an herbivore. So that brontosaurus walks around eating lots and lots and lots of leaves from trees and other vegetables and other plant life. And those plants, where did they get their energy from? Right? They did photosynthesis in order for them to make that glucose that we talk about to get their energy. And how did they do that? Right? They got that energy to do photosynthesis from the sun. So this brings us all the way back to the name of this unit, which is unleashing sunlight. So that oil, that coal, that natural gas that we use to burn, right, and release energy to boil water to make a generator turn to get electricity came from, right, a dinosaur that ate plants, and those plants got their energy from the sun. So the energy stored in coal is stored sunlight. It's very strange when you think about it. So let's talk a little bit about one other form of non-renewable energy, and that is nuclear energy. We're not going to spend too much time on this because the process of using nuclear energy is nuclear physics, which is, a bit more than we want to talk about in middle school science. But the basic here is you're still using these radioactive substances to boil water, right? It seems pretty primitive, but it's very effective because I'm now recording this benchmark while the iPad is plugged into an outlet. All right, and that outlet got its electricity from a power plant, and that power plant got its electricity from a generator spinning, and that generator got the energy it needed to spin, right, from steam, and that steam was created from the boiling of water, and the energy to boil that water came from either fossil fuels, right, or nuclear energy. So nearby the Turner household, we have a nuclear power plant, Indian Point Nuclear Power Plant. And this is the process by which they make electricity for most of Westchester and Rockland County and about 30% of the energy for New York City. It's shutting down and being decommissioned is the fancy word for it. But for many, many decades, Indian Point Nuclear Power Plant generated electricity for all of the surrounding areas, right, including one of the largest cities on Earth, right, through using this idea of breaking down radioactive substances, splitting them apart, and that process is called fission, nuclear fission. And when you do that, when those radioactive elements, those atoms fall apart, they release more energy than you could even possibly think of. And doing so, again, it sounds crude and primitive, boils that water to make the steam that makes the generator spin, which causes electrical current to flow through those wires. It seems oddly and eerily simple, but obviously it's incredibly effective. So nuclear energy, another form of non-renewable energy. Okay, so we've talked about non-renewable energy resources, right? Fossil fuels and nuclear energy. And even though fossil fuels technically are renewable, they're not renewable in the sense of a human timeline, right? These things took millions and millions and millions of years, and the way that humans use these non-renewable resources is too fast for it to ever be replaced in enough time for us to keep it and make it sustainable. And sustainable is a fancy word that just means that we can use it almost as often as we can replace it, right? So that it sort of creates a loop of using it, making it, using it, making it, using it, making it, that sustains us so that we don't have to keep pulling resources from the earth that can't be replaced in a fast enough time. So looking at renewable resources, these are kinds of energy sources that can be found and replaced quickly. The issue is sometimes it becomes difficult for us to capture them, right? Or it becomes expensive and costly. And that's sort of where the balance happens here. We can get fossil fuels super fast and relatively cheap because we have the technology to do it, but we're going to eventually run out. And the issue is people don't want to spend the money or the investment of time and energy into researching and refining and making the renewable resources easier to use, simply out of convenience, right? So it's the reason why we still drive cars that use gas, even though we have lots of vehicles that could run solely on electrical energy and renewable resources. So hopefully we're going to be making that shift as a human race soon. All right, so let's talk about renewable resources. The first of which is solar energy, right? That is a giant ball of nuclear fusion and fission 93 million miles away from us. The sun, it is about 110 times the size of Earth, 93 million miles away from us. The light that leaves it takes about 8.5 minutes to get to us from the sun, and man, that packs a huge punch of energy. And that energy comes in the form of these little packets of light called photons. So many trillions of photons reach the Earth every second. And we can use that energy to heat up water or keep us warm. If you have been outside in the springtime or the summertime, you can feel the warmth coming from the sun directly on your skin. And the idea behind using solar energy is just that. We can harness that energy, right, to do work for us. And the idea here is that that work should be able to take the form of anything other than just heat. And we have to find a way as humans to figure that out. And we kind of have. So the idea here with photons is that we can use it to heat. And if you've ever made like a solar oven by taking aluminum foil or some kind of shiny object and folding it and bending it so that the light keeps bouncing around inside of it, you can cook with a solar oven. You can also heat up water in pipes and use that hot water to do lots of things throughout your house. But those are limited in what they can do, and there's definitely not enough power generated from doing that particular process in order for us to, keep our lights on and run all of our electrical outlets throughout our house. But we do have some new technology in recent years that we've come across that has been able to harness the power of the sun. So again, coming back to those little packets of energy called photons, we use that energy to heat water or keep us warm, and it can also be used to generate electricity. As humans, we have become wholly reliant on the concept of electrical energy. So in order for us to make solar power work for us, right, we need to be able to find a way to get that solar energy to create electricity, right? So the problem, only about a half of a watt per square meter hits the surface of the Earth. We need to find a way to take that energy and sort of store it in a battery. And we have, as a result of that, ingenious humans that we are, we've come up with solar panels. Right? So what is a solar panel? Solar panels are relatively complicated in how they're designed and built. Really ingenious concept of engineering. But to make it a bit simpler, let's just talk on a basic level about what a solar panel is. These are devices that are made of one layer of a metal, a sheet of metal, and then one layer of something called a semi-metal. All right, so there are different elements that exist on the Earth and throughout the universe. And some of them are classified as metals. You're familiar with them. Things like copper and nickel and cobalt and iron and mercury. And then we also have other classifications of elements called nonmetals. These are things like oxygen and carbon and sulfur and any of the sort of elements that are gases. Right? So we also have kind of wedged in between them elements that are not metal and not metal. And so, not to use a double negative, we call them semi-metals, right? They're kind of metal, they're kind of not. And they have properties that kind of, straddle the line in between metals and non-metals. The idea here, though, is that when sunlight hits these panels that have a layer of metal and a layer of a semi-metal, there are electrons, and these are one of the three basic parts of an atom. We have electrons that get excited and move. They jump from one atom of a metal to another, or they jump across the two layers, and that's where the ingenuity, right, and the amazing engineering that goes into solar panels takes place. Right? The light from the photons from the sun hit a layer of metal and excite, give the energy to those electrons, and those electrons will jump from the metal to the semi-metal. And when they do that, they create an electric current. So electric currents are electricity. And we have ways of storing that electrical energy, that potential energy inside of a battery connected to a solar panel, or we can use it right away. And you'll see lots and lots and lots of solar panels on roofs throughout the area because it's becoming more and more popular as far as technology is concerned. And in many cases, homeowners will take out a loan to get solar panels put on the roofs of their houses because they're kind of expensive. We're talking more than $50,000 to put solar panels on the roof. And so they'll take out a loan and they'll pay off, all right, the bill that they have for those solar panels. And they'll do that either by paying it directly, or they'll do that by hopefully having their house in a space where sunlight hits it for a long period of time. And the longer it hits the solar panels, the more energy can be used either to power the electrical devices in their house, or any extra excess energy, the electricity that's made, can actually be sent back to the power companies. And so some people actually end up, instead of getting an electrical bill, right, from Con Edison or another power company, can sometimes get a check, right? And then once you kind of balance that out, and you learn the best way to save your energy and get the most sunlight out of your solar panels on your roof, you can end up receiving money every month for having those solar panels on your roof, which help pay them off. And once they're paid off, you could actually start making money off of the fact that you have solar panels on your roof. It's a very enticing concept for many people, so they are becoming more and more popular these days. Okay, so solar power, definitely something to pay attention to. It's going to be, if it isn't already, an incredibly popular form of renewable energy moving forward. Another one that is kind of based on how close we are to bodies of water is hydroelectric power. So the sun is involved in this again, right? Unleashing sunlight's the name of this unit. So far, we are talking about solar power, directly using the energy from the sun to get electricity. Here with hydroelectric power, we use the energy from the sun a little bit indirectly. So thanks to the sun and the concept of gravity, we can take energy of moving water. So the idea here is the water cycle. And you saw the water cycle in our last unit. The sun heats up the water evaporates, it rises into the sky where it becomes a cloud, and eventually those clouds become so saturated with water that that water condenses and, because of gravity, falls back down. That's our water cycle. So the idea here is that as that water falls back down, it goes through mountains and streams and rivers and collects into larger bodies of water. And eventually, those bodies of water can be sort of blocked off with a hydroelectric dam. And the water can be held back so that when it does get released to fall down, potential to kinetic energy, right? You can use the power, the energy of that falling water to move a generator. That generator can make electricity. What an amazing concept. There's no pollution. It's the energy of the sun and the law of gravity helping us to create electricity. Right. One drawback, though, to hydroelectric power is that you're holding back bodies of water and you're messing a bit with nature. Right? So wildlife can be negatively affected by these hydroelectric dams, and they're big and costly. So we as humans have to decide whether or not it's worth the disruption to wildlife to have these. Okay, so let's talk about wind now. Right? We can use windmills to pump water, as well as just directly generate electricity. So let's talk a little bit about wind real quick. It's almost always around, and at higher elevations and in certain places on Earth, it's everywhere all the time. We can use the energy from wind to push turbine blades. And these turbine blades are connected to a generator. So we get energy directly. We don't need steam. We don't need to boil or burn anything. We can take these giant windmill turbine blades and spin them to spin that electromagnet inside of the generator to make the coils of wire create a current of electricity, and poof, we get electricity right away. So here's the issue. These turbines are big, right? Sometimes they're 400 feet tall and 200 feet wide. They also move at speeds of 100 miles an hour. They can be loud and noisy, and they can be a danger for birds who get anywhere near them. You can see them, and if you've ever seen a wind turbine blade, you'll see they look like they're moving very slowly, but that's because you're far away and they're super big. You get close enough, you can hear those things spin rather loudly, and they move much faster than you think. So those poor birds don't stand a chance if they get anywhere near them. The other issue is people don't necessarily like the way that they look, and they can sort of clog up the skyline and make beautiful views, right? Sort of not look as nice. And so we as humans have to think about whether or not that's a sacrifice we can make, because wind is always around, and it's a very easy way for us to get electricity. So let's talk now about tides. Right? And we're not talking about the laundry detergent here. We're talking about the flow of water in huge bodies of water like oceans and really big lakes and rivers. So the moon, although it is a super cool shiny rock in the sky, it's not just that. And by the way, the moon's not shiny because it makes its own light. That light comes from the reflection of sunlight off of the surface of it. Right? So because it's so big and so close to Earth, gravity is a thing. All right? Those two large bodies of objects push and pull on each other. And as a result of that, the moon is stuck in orbit around the Earth all the time. And at different times of day, it ends up closer to some parts of the Earth and farther away from others. The result of that is that it pulls, right, this constant force pulls and pushes the water in our oceans and large lakes and rivers. As a matter of fact, our Hudson River is affected by the tides. There are certain times of the day where you can see the Hudson River closer to the shore, and other times of the day when you can see it pulled farther away from the shore. Now, the idea here is that this constant and reliable flow of huge amounts of water back and forth due to the moon's gravitational pull on us and our gravitational pull on the moon, right, we can make upside down, basically wind turbines that we stick underwater, and as that water moves back and forth, it spins those turbines. And those turbines, of course, are connected to a generator, and that generator is an electromagnet that spins around a coil of wire that creates electricity. So yet again, another form of renewable, constantly available to use energy, very reliable, that allows us to get electrical energy. The issue, of course, is people who live in Iowa don't have large tidal affected bodies of water. So this form of renewable energy isn't necessarily effective for them. Okay. Now, moving on. Geothermal energy is another form of renewable energy because we got a whole lot of liquid hot rock underneath the surface of the Earth called magma. And we can take the tremendous amount of heat energy that's coming from that magma and use it to boil water to make steam. So here's our common thread again, making that steam to turn a generator. And we can take the heat energy from beneath the surface of the Earth to do that. And it kind of is a form of energy that we don't see running out anytime soon. So we have places like Italy and California, and even here in the Hudson Valley, where we can get geothermal energy. And the idea here is that these places in particular are good for geothermal energy because of this concept called plate tectonics. And that's not a topic we're going to talk too much about in 6th grade science. You'll see it again later on in 8th grade science. But imagine the Earth as kind of like a layer of wiggly jiggly jello, and then a whole bunch of puzzle pieces wrapped around the Earth, sort of flowing and moving on top of that layer of wiggly jiggly jello. Over time, and due to lots of conditions inside the Earth, the wiggly jiggly parts, right, of the surface of the Earth take those puzzle pieces and can kind of move them. Right? Those pieces could separate, they could slide across each other, they could bump into each other. And the idea is any place where the pieces come together, right, are places where we have easy access to all of that wiggly jiggly stuff, which is basically the magma underneath the surface of the Earth. We can get the heat energy from that. So we have these plate boundaries. Right? So California, Italy, and even here in the Hudson Valley, there are boundaries where the crust, the surface of the Earth, right, meets other big chunks of crust from the surface of the Earth. And there's kind of a space in between them where we can get in there and pull the heat energy out of. By the way, it's also why we can occasionally register earthquakes in this area, as those plates can often build up pressure between them and then suddenly slip or pull apart or ram into each other. But that's, again, a topic for 8th grade science. Let's talk a bit about biomass really quick. So the idea behind biomass is we don't want to wait for dead dinosaurs and plants to make that fuel for us through fossil fuels. So can we take stuff that is readily available and grows like crazy here on Earth and burn that stuff and get our steam to turn our generator to make electricity that way? Right? So better than burning really old dinosaurs, let's burn not so old things to get electricity. So we can use plants like sugarcane and switchgrass, which grow super fast, and burn them to release energy. We can also use vegetable oil from fast food restaurants for the same purpose. So yes, you can use old French fry oil from McDonald's or some other fast food restaurant to power our cars. right? And don't take any of that vegetable oil you got laying around from food you cooked from dinner and pour it into your parents' cars. The car will stop working. So vehicles that can use this French fry oil or other used vegetable oil have a specific filter, and they have a modified converter that uses that energy differently as it tries to burn the chemical energy stored in that French fry oil or vegetable oil to help the engine run. So cars are designed to run on gasoline or diesel fuel, not vegetable oil, unless you convert that. Right? So again, a word of warning: don't take used French fry or vegetable oil and pour it into your parents' car. It's not going to work. But if you do end up converting that, it's really neat. I have been driving behind vehicles that do have that conversion in their car, and the exhaust that comes out of the back of the vehicle smells like French fry oil. It's pretty interesting. If you haven't noticed, out of the 6 different kinds of renewable energy that we've talked about so far, many of them have one thing in common, right? And that one thing in common is the sun. Right? That's incredibly important. Why is it incredibly important? Because the sun isn't going anywhere. We have hundreds of millions of years of life left in the sun. Not life as in the sun is living, but life as in we can pull the energy coming from the sun. This giant nuclear reactor, 110 times the size of the Earth, is constantly providing us with energy. Okay, so why not use it? And think of all the different ways that we use the sun in renewable forms of energy. Right? That sun is used to grow plants that we can use to burn. That sun is used on solar panels that we can use to generate electricity. That sun is used to heat up water so that it can condense in clouds and fall back to Earth. That sun is used to unevenly heat our air to create wind. So the sun is involved in so many different possible ways to get renewable energy. It's sort of time for us to start thinking about really inventive and ingenious ways of utilizing it so that we don't, number one, pollute our planet, right, from burning fossil fuels, or run the risk of running out of fossil fuels and then have no source of energy. And finally, I want to talk a little bit at the end of this first half of our series of benchmarks here on unleashing sunlight about some human conservation efforts. Here are some, or 3 in particular, very notable efforts on our part as humans to try to make a positive difference in the world to offset some of the negative stuff we've done. In 1890, John Muir's work as a nature writer actually leads to the establishment of Yosemite National Park. Right? And our national parks are beautiful things to behold. If you ever get a chance to travel across the country to visit these parks, efforts from people like John Muir are the result of those being protected lands. Even though they are rife with resources that we could use, they have been established as protected, and therefore nothing can be done to them other than letting them be what they are as a natural resource. In 1903, President Teddy Roosevelt establishes the first national wildlife refuge in Florida, right, helping us keep places like the Everglades, which is another incredibly abundant and diverse section of the United States full of wildlife and probably species of animal and plants that have yet to be discovered exist there. So we need to keep them safe. And finally, to point out, in 1962, Rachel Carson writes the book Silent Spring, which talks about an incredibly important concept called bioaccumulation. And the word accumulation means to build up. So the idea was she found this chemical, DDT, that was used sort of as a pesticide spray. So we were using this chemical to keep bugs and other fungus and issues off of our plants as we grew them, our vegetables and fruits, so that we could have an abundance of fresh fruits and vegetables for ourselves. They would be sprayed. The issue was that this chemical would basically be absorbed by the plant. And then animals that would eat those plants would have that chemical go into them. And then animals that would eat the animals would have the chemical go into them. And this chemical would build up and build up and build up, using basically the same kind of concept as the energy pyramid, but kind of in like a twisted, weird way. So you would get these apex predators, these tertiary consumers like bald eagles, right, who would eat animals that would eat other animals that would eat, right, plants that had this chemical on them, and there would be so much of this chemical DDT inside of them that they would get sick and die. And a famous case was with bald eagles, and the chemical would actually make the eggshells of the bald eagle eggs so fragile and thin that they would crack and break, and we were having a major issue with the population of bald eagles. So her book, Silent Spring, brings into this idea that chemicals that we put out in nature build up over time inside of all of the organisms that live in nature, and can cause a major issue. Even though you're not using a lot of it at once, it builds up. And so she got the chemical banned permanently forever, and brought to light the idea of using chemicals and pesticides in responsible ways or not at all. So this concludes our first benchmark for renewable energy. Our second benchmark will pick up with the idea of the sun, moon, and earth and their interactions with each other. And we'll talk a little bit about how renewable forms of energy come about, not just from the sun directly, but through the earth and the moon and the sun interacting with one another. So thanks for watching.